We'll give him a second. Hey, Sherry, how you doing? Sherry, great testimony. Thank you. Okay. All right, Dr. McCormick, welcome. I think we're going to go ahead and get started here. The committee will now come to order. Without objection, the chair is authorized to declare recesses of the committee at any time. Members are reminded that this committee's practice is to submit letters and other items for the record to the committee before seeking UC to insert such items into the hearing record. This allows the committee to ensure that such items meet the rules of decorum and verify their length and provenance, and that they do not contain sensitive, proprietary, or controlled information. The chair reserves the right to object to any UC request to insert items into the record that are not provided in advance. Welcome to today's hearing entitled Assessing U.S. Leadership in Quantum Science and Technology. I recognize myself now for 5 minutes for an opening statement. Thank you for joining us today in our hearing, Assessing U.S. Leadership in Quantum Science and Technology. I would like to thank our esteemed panel of witnesses for being here this morning and their continued service to the federal science enterprise. We're looking very much forward to your testimony. The Trump administration has identified quantum science, technology, and engineering as a top research and development priority and the core pillar of U.S. scientific leadership. President Trump's first term marked a turning point in federal quantum policy with the enactment of the National Quantum Initiative Act, elevating quantum to a national focus. These investments reflect a long-term strategy for American innovation in quantum science, technology, and engineering, and I remain committed to working closely with this administration to carry these priorities forward. The federal government plays a central role in supporting fundamental research, large-scale infrastructure, and addressing the long-term challenges that drive innovation in quantum science. These investments lay the foundation for breakthroughs in quantum computing, sensing, and communications. The private sector then plays a vital role in translating those breakthroughs into scalable and commercially viable applications. As quantum technologies mature, maintaining U.S. leadership will require sustained investment in fundamental research and progress on key engineering challenges and development of the enabling technologies that support the broader quantum ecosystem. This includes strengthening research consortia and expanding test beds and infrastructure, improving advanced manufacturing, and ensuring quantum systems can be deployed in real-world environments. Quantum science also has direct implications for national security and cybersecurity. Preparing for post-quantum cryptography and defending against emerging cyber threats will be absolutely essential as these technologies evolve. With adversaries around the world investing heavily in quantum capabilities, the United States cannot afford to fall behind in the global race to quantum supremacy. The National Institute of Standards and Technology, or NIST, has played a leading role in securing our post-quantum future. In August of 2024, NIST published its first set of post-quantum cryptography standards to safeguard a wide range of digital information, from sensitive government communications to everyday e-commerce transactions, against quantum-enabled cyber threats. This milestone builds on decades of expertise in measurement science and information technology and provides essential tools and standards for a secure quantum-enabled future. And while the National Aeronautics and Space Administration is not a formal member of National Quantum Initiative, the agency has made meaningful contributions through targeted investments. NASA has pursued quantum-enabled technologies for space science and precision measurement, developing tools and instruments that push the boundaries of fundamental physics and address complex computational challenges. The Department of Energy is also driving progress in quantum science through initiatives such as the Genesis mission and the newly established Office of Artificial Intelligence and Quantum, while supporting research across quantum computing, sensing, materials science, and fundamental physics. Like many emerging technology sectors, the quantum industry faces a growing demand for skilled talent. The National Science Foundation and DOE Quantum Centers, established under the National Quantum Initiative Act, have made significant strides in developing educational programs, training initiatives, and industry partnerships to help meet the workforce needs. These efforts depend on sustained federal support, and I welcome the opportunity to hear from our witnesses today about the work that is underway. Both my staff and Ranking Member Lofgren's staff are working collaboratively on a bipartisan reauthorization of the National Quantum Initiative. This effort seeks to reinforce U.S. leadership in quantum science, technology, and engineering, address workforce challenges, and accelerate commercialization. Today's discussion will inform and guide our legislative work. I am interested in our witnesses' recommendations on how Congress can strengthen the National Quantum Initiative over the next 5 years. I want to thank you again, witnesses, for being here today. I'm looking forward to a productive discussion, and I yield back, and I would now like to recognize the ranking member of the full committee, Representative Lofgren of California, for 5 minutes.
Well, thank you, Chairman Babin, for today's hearing, and I'd also like to welcome our panel of distinguished witnesses. For years, the United States enjoyed being the global leader in quantum information science in terms of both research output and investment across every quantum application and modality. Our leadership was built upon a foundation of investments and efforts at every level in academia, industry, and our federal government. The U.S. government has been the primary supporter of openly published quantum research, totaling nearly $1 billion in investments in 2023. However, we're now facing a peer competitor to the United States in quantum applications. In 2024, the Chinese Communist Party invested more than 4 times what the United States did in quantum R&D. In 2025, the CCP announced a $138 billion fund to support their public-private partnerships in emerging technologies, including quantum computing. And in terms of quality of research and technology development, China has caught up. Chinese industry leads in certain global market segments, including quantum communications. Now, U.S. leadership in quantum technology stands, I think, at an inflection point. We can renew our commitment to leadership through actions, not just words, or we can be left behind. To start, it's critically important for this committee to take up a reauthorization of the National Quantum Initiative Act, and as the chairman has just said, we're excited to be working together on this bill. And I want to thank you, Mr. Chairman, for your leadership in this matter. Maintaining global leadership in quantum technology also requires us to avoid getting in our own way. Really, the chaos that we're seeing in our federal government right now only emboldens our adversaries. If we're going to win the race on quantum, we need each of our federal agencies, including the National Science Foundation, National Institute of Standards and Technology, the Department of Energy, and NASA, to be fully staffed and resourced. Congress, fortunately, rejected the Trump administration's destructive budget proposal and provided strong support for the agencies critical to U.S. quantum leadership. And I hope the President's fiscal year 2027 budget request is not a repeat of this year's. If we're going to win the race on quantum, we can't only fund programs with quantum in their name. Many fields and disciplines make up the backbone of U.S. quantum research and the quantum workforce. A cut to physics is a cut to quantum. A cut to mathematics is a cut to quantum. A cut to engineering is a cut to quantum. We need more federal support to generate interest in these feeder fields, not less. If we're going to win the race on quantum, the United States must have a quantum-capable workforce. Unfortunately, the Trump administration is simultaneously turning away foreign talent while also canceling programs to train domestic talent. During our previous quantum hearing, I highlighted several quantum workforce programs at universities across the country that had their grants terminated. And since that time, the administration has increased pressure on foreign talent through visa fees, rejections, and intimidation. If the United States is not the destination of global quantum talent, then other nations certainly will be. Finally, if we're to win the race on quantum, we have to address the severe supply chain challenges that are preventing industry and academia from building quantum machines in America. The President's unilateral, and I think likely illegal, imposition of tariffs have created additional costs and vulnerabilities for new and innovative domestic industries like the quantum industry. Quantum supply chains are thin, and oftentimes the only suppliers of critical equipment and critical materials are offshore. Tariffs on this equipment doesn't help American manufacturers, it hurts them. My staff talked to one quantum company last year that had to pay a 7-figure tariff on a single piece of equipment from Europe. And the chaotic manner the administration has approached tariff policy has made this worse. Just the other day, President Trump threatened additional tariffs on Europe because of his weird Greenland obsession, and then yesterday he appeared to back off on that. This chaos is forcing quantum startups to question whether America can be a reliable base of manufacturing. I look forward to working with my colleagues on both sides of the aisle to address the challenges facing our quantum industry, and hopefully to find a more willing partner in the executive branch in this endeavor. I look forward to hearing from the witnesses about these challenges and others during today's hearing, and I want to thank you, Mr. Chairman, and my time is expired. I yield back.
Yes, ma'am. I want to thank you. Now I'd like to introduce our witnesses for today. And our first witness today is Dr. James Kushmerek. Is that the way you pronounce it, right? Yes, sir. Director of the Physical Measurement Laboratory at the National Institute of Standards and Technology. Welcome. Our second witness is Dr. Saul Gonzalez, Deputy Directorate, Head of the Directorate for Mathematical and Physical Sciences at the National Science Foundation. Welcome. Thank you for being here. Then our third witness is Dr. Mark Clampin, Deputy Associate Administrator for the Science Mission Directorate at the National Aeronautics and Space Administration. Good to see you again. We appreciate your service. And then our final witness is Dr. Tanner Crowder, Quantum Information Science Lead for the Office of Science at the U.S. Department of Energy. Welcome. I now recognize Dr. Kushmerek for 5 minutes to present your testimony, sir. You are now recognized.
Chairman Babin, Ranking Member Lofgren, and members of the committee, I am Dr. James Kushmerek, Director of the Physical Measurement Laboratory at the National Institute of Standards and Technology, or NIST. Thank you for the opportunity to appear before you today to discuss NIST's leading role in advancing quantum information science and technology. This hearing comes at a critical time. We are in a fierce international competition for continued leadership in quantum information science, with countries like China making significant investments in quantum research and development. The U.S. cannot afford to take its foot off the gas. Quantum science is the epitome of precision measurements, and thus NIST has been a leader in quantum science research for over 50 years. NIST's premier contributions in quantum science have even been recognized by 4 Nobel Prizes in physics. Our long history of foundational research has made NIST the world's leading institute for quantum technologies. Technology spun off from NIST research has seeded America's quantum industry, ranging from large corporations to startups, producing key technology platforms that are driving today's emerging quantum industry. NIST actively contributes to and facilitates U.S. industry engagement in the standardization of quantum technologies, including administering the U.S. Technical Advisory Group on Quantum Technologies. Additionally, NIST played a leading role in establishing NMI-Q, a global initiative consisting of the National Metrology Institutes from the G7 countries and Australia. The National Quantum Initiative, known as NQI, recognized the importance of quantum information science and technology. Through the NQI, NIST has nearly doubled the size of its quantum portfolio, increasing research, coordination efforts between NIST and other agencies, and redoubling efforts in training of a quantum-ready workforce. NIST's research programs have shaped and trained a significant portion of today's quantum workforce. Further, as directed in the founding NQI legislation, NIST established the industry-led Quantum Economic Development Consortium, QEDC. The QEDC is the primary vehicle for industry to come together to identify and address roadblocks for the commercialization of quantum technologies in the U.S. To maintain American leadership, we need to continue to prioritize fundamental research, infrastructure, and applied research to develop and scale quantum technologies. Quantum computing, the most anticipated use of quantum technology, will be able to solve problems beyond today's classical computers and affect nearly every sector. However, the power of quantum computing in an adversary's hands also threatens public key encryption, which underpins secure, trusted digital communication. In 2024, NIST released the first 3 post-quantum encryption standards, ushering in a new age of cybersecurity and laying the foundation to protect trillions of dollars of global commerce. NIST, given our unique expertise of working with industry throughout the R&D pipeline, can unleash the economic benefits and competitive advantages of U.S. businesses by adopting an acceleration model focused on the manufacturing of new quantum sensors, manufacturing of scalable high-performance quantum components, and development of quantum networks, including deployed quantum talks. With this holistic approach, NIST will enhance its core research and standards program by developing quantum technologies and conducting fundamental research in quantum sensing and quantum computing with the goal of identifying and eliminating roadblocks for practical deployment. At the same time, NIST will create accelerators, adaptive and flexible industry partnerships to rapidly develop and manufacture quantum and quantum-enabling commercial products. This effort will utilize co-development with industry to overcome major engineering challenges and manufacturing barriers that limit the current performance, scalability, and commercial viability of quantum industry products. Thanks to the wealth of fundamental research knowledge, the American entrepreneurial spirit, and the NQI, the U.S. is a global leader in quantum technologies. While the nation is currently in a strong position, we cannot afford to be complacent in the face of global competition. With the reauthorization of the NQI and continued strong congressional support for NIST research, we will ensure sustained U.S. leadership in this rapidly developing sector and ultimately win the quantum race. Thank you for the opportunity to testify today on NIST's activities, and I look forward to answering any questions.
Thank you, Dr. Kushmerek. Appreciate it. Now I'd like to recognize Dr. Gonzalez for 5 minutes to present his testimony.
Thank you. Chairman Babin, Ranking Member Lofgren, and members of the committee. I'm Dr. Saul Gonzalez, Deputy Directorate Head for the Mathematical and Physical Sciences Directorate at the U.S. National Science Foundation, where I help lead NSF-wide efforts in quantum information science. It's an honor to be with you today to discuss the vital role has played in the many exciting advancements in QIS, how these efforts have been bolstered by the National Quantum Initiative Act, and how we continue to push the frontiers of QIS. The work is done in close collaboration with partners across the federal research enterprise, including through the NQI-established NSTC Subcommittee for QIS, which NSF co-chairs. This subcommittee brings together relevant agencies, including the 4 represented here today. Progress depends on our shared long-term vision, and no single agency, sector, or institution can build the quantum future alone. The 2018 NQI recognized the urgency of maintaining U.S. global leadership in QIS and its applications and technologies. That urgency has only grown over time as the global race has accelerated, fueled in part by the ambitions of our global adversaries, such as China. The U.S. has the ability, the talent, and the infrastructure to not simply maintain, but to grow our leadership across all critical and emerging technologies, and at NSF we consider this a core part of our mission and an economic and national security imperative. NSF supports research across all fields of STEM and at all levels of STEM education. Our investments fuel groundbreaking discoveries, accelerate translation of research results to the market, and support the U.S. workforce. Our multidisciplinary approach is not only well-suited to QIS, but also to other emerging technologies like AI and biotech. Early NSF investments in QIS have been critical for U.S. leadership and have laid the foundation for the second quantum revolution that is now taking place. Not only has that foundation fueled numerous Nobel Prizes, but it has built a community of thousands that is now founding companies that contribute billions of dollars to the U.S. economy. With decades of prior investment to build upon, NSF was well-positioned to contribute to opportunities presented by the 2018 NQI Act. NSF's vision under the NQI is focused on 3 goals: expand our fundamental understanding of quantum phenomena and systems, deliver integrated proof-of-concept devices, applications, and tools that show quantum advantage, and build and support a quantum-smart workforce. NSF's accomplishments under the NQI include the establishment of 5 large multidisciplinary centers focused on addressing major challenges in computing, in sensing, and networking. NSF is also establishing a nationwide infrastructure platform for testing, piloting, and prototyping quantum technologies with a focus on at-scale demonstrations. These platforms are designed to de-risk and smooth the transition from basic science and engineering to the market. We continue for innovative ways to accelerate translation from lab to market and to grow the American STEM workforce. For instance, in the NSF Engines programs, 2 finalists in the current competition are advancing QIS to drive regional economic growth and job creation. Since 2018, our efforts have nearly doubled the number of faculty and students working on NSF QIS projects, and still the supply of talent is not keeping up with industry's demand. As I conclude my remarks, I think it's appropriate to offer an analogy to the incredible advances we've seen in artificial intelligence. It took decades of research to develop the breakthroughs necessary to turn AI into the $500 billion market that it is today. We are at a similar inflection point in QIS. Technological developments in QIS have accelerated recently, and we could be just a few breakthroughs away from a major transformation in this field as well. The NQI provided a solid foundation for how the U.S. can win the global race for quantum technology future, calling upon NSF to leverage our unique collaborative, multidisciplinary approach to accelerate fundamental research, pioneer new applications, fuel transformational solutions, and foster the talent that makes these innovations possible. NSF is committed to these efforts alongside our partners across the interagency and in collaboration with Congress and this committee. Thank you for the opportunity to appear before you today, and I look forward to your questions.
Thank you, Dr. Gonzalez. Now I'd like to recognize Dr. Clampin. You're recognized, sir. Thank you.
I am Dr. Mark Clampin, Deputy Associate Administrator of NASA's Science Mission Directorate. NASA is at the forefront of putting quantum science into action in both quantum computing and quantum sensing. The agency leverages the unique environment of space to drive quantum space breakthroughs. These advanced technological innovations, such as navigation, computing, communications, and scientific discovery. NASA is especially focused on quantum sensing to address its exploration and scientific opportunities. Quantum sensing is not new to NASA. As early as 1964, NASA's Mariner 4 was the first U.S. mission to fly a quantum sensor, an optically pumped vector magnetometer. We use vector magnetometers to tell us which way the magnetic field points and its strength to study planetary magnetic fields, solar wind interactions, and space weather. So Mariner 4 was the first spacecraft to explore Mars and gave humanity its first close-up glimpse of another planet, setting a standard for U.S. leadership in this scientific area. Just recently, NASA flew on the XRISM X-ray astrophysics mission the first imaging quantum sensor. This sensor is known as a microcalorimeter and was developed by the Goddard Space Flight Center. It measures photon energy so precisely that it's ideal for applications like X-ray astronomy, where it helps NASA better understand the nature of black holes, neutron stars, and galaxy clusters. NASA is at the tip of the arrow for America's advanced technology strategy for quantum sensing space applications. It's our job to go first and confront the hardest technical problems and create applications. We partner with industry, other government agencies, and universities to take U.S. quantum technology even further. We pioneer their use and also minimize risk so that the United States private sector can then adopt and scale them. By developing these technologies to solve exquisitely difficult problems, NASA ensures that there's a sustained pipeline of innovation for new space-based missions and industry that will achieve our agency objectives for the benefit of all, also while helping to keep our astronauts and spacecraft safe and operating in space. I want to emphasize especially that NASA develops quantum science for use in sensing applications. Another example is our Cold Atom Laboratory, which has been on the International Space Station since 2018. The International Space Station is and has been the world's premier science-based laboratory. It allows scientists working with astronauts, for example, to examine Bose-Einstein condensates, a unique state of matter at temperatures just above absolute zero. Studying cold atom physics is really a key to the building block in developing next-generation quantum sensors. Today, NASA is building on the knowledge we learned from the Cold Atom Lab to fly a space instrument that can sense Earth's gravity 10 times better than anything we have today, a quantum gravity gradiometer that relies on a technique called atom interferometry. By studying the ultra-precise measurements of the Earth's gravitational changes, NASA will be able to map precisely where water is and isn't, and better support applications such as drought monitoring, water management, and the determination of flood potential across the globe. This is just one of several areas across NASA Sciences where the agency sees exciting prospects for disruptive advances as we prepare to send humanity on its journey to the moon and onwards to Mars, and then beyond for the first time in our history. I look forward to seeing how quantum science will play a major role in ensuring that both astronauts and spacecraft are protected and thriving on their journeys to the extreme environments beyond our home planet. Thank you for the opportunity to testify, and I welcome your questions.
Thank you, sir. And now I'd like to recognize Dr. Crowder for 5 minutes.
Good morning, Chairman Babin, Ranking Member Lofgren, and esteemed members of this committee. I'm honored to appear before you today to discuss quantum information science and technology and the transformative role that it plays across the Department of Energy's portfolio. This field is deeply important to both the department and our national prosperity. I'm grateful and appreciative of this committee's continued support for the advancement of this field, as well as science and technology broadly. I'm Tanner Crowder, and for nearly 20 years, I've worked in this field as a federal researcher, senior policy advisor, and now quantum information science lead and senior advisor in the Office of Science, Department of Energy. Our work in quantum information science and technology spans the DOE programs and includes the advancement of fundamental science, quantum computing, quantum sensing, and quantum communications and networking. The DOE brings unique resources and a team science approach to secure American dominance in this field, leveraging our suite of user facilities and some of the most advanced technologies and computational abilities available to the American research and industrial ecosystem. The National Quantum Initiative Act was a significant milestone for American leadership in science and technology. This legislation delivered a national strategy, mobilized dedicated and sustained departmental efforts, and launched several new center-scale flagship activities. DOE established 5 multidisciplinary national QIS research centers in response to the NQI Act. Each center is led by a national lab, and collectively they bring together academic institutions, industrial partners, and drive discovery. In the first 5 years, the DOE centers laid the groundwork to deliver scientific breakthroughs across high-energy physics, material science, computing and networking, and biosciences. Last November, the department renewed its commitment to the centers to accelerate the advancement of quantum technologies and tackle larger-scale, focused research efforts with a high potential to unlock new possibilities in both technological development and basic science. In addition to the centers, DOE advances quantum information science technology through its core research programs, testbeds, and user facilities. The DOE's portfolio builds a foundation for the exploration of quantum information science technology and acts as a powerful catalyst for the entire ecosystem, addressing key roadblocks to quantum utility. As a result of the federal investments and sustained support from this committee and Congress, American quantum technology community is embarking on a new chapter, one that in addition to supporting fundamental R&D, can drive capabilities such as quantum-centric supercomputers that will provide a paradigm shift for exploring new scientific frontiers. Delivering these novel capabilities involves substantial infrastructure and technical expertise from quantum information scientists and engineers, as well as domain scientists that will use this new technology. Maturing quantum technologies into fully functional scientific instruments for America will require careful coordination among federal agencies, scientists, engineers, manufacturers, and industrial performers. This effort will explore new scientific discoveries, public-private partnerships, and a robust supply chain. DOE is well positioned to support the development of these novel capabilities. Our national labs have multidisciplinary experts that excel in balancing open science, proprietary R&D, and national security missions. Together, we have expertise and infrastructure to bring first-of-a-kind scientific instruments and computing systems online, maintain these systems, and develop a broad user community. A whole-of-government approach with the support from the DOE and the national labs to responsibly scale quantum computing technologies for scientific discovery would position America to lead in the convergence of quantum computing, artificial intelligence, and high-performance computing. Like the Exascale Computing Initiative, it would catalyze industrial efforts by setting clear targets and strategic guideposts to align the sector, stimulate competition, and forge public-private partnerships to demonstrate the first generation of error-corrected quantum-centric supercomputers that can deliver scientific utility. This vision integrates with the recently launched Genesis mission to unleash a new age of AI and quantum-accelerated innovation and discovery, solving the most challenging problems of the century. The resulting capabilities, talent, and infrastructure will serve as a competitive differentiator, a stabilizing force, and an incubator for American industry across all scales, and achieve the ambitious goal of dramatically accelerating scientific discovery and to significantly increase the productivity and impact of R&D in America. Quantum information science and technology hold great potential to unlock a new era in American innovation and economic competitiveness, offering the promise to solve some of the world's most pressing challenges. The National Quantum Initiative Act recognizes this great potential. Its reauthorization can usher in the next chapter, ensuring that we maintain leadership and once again maximize the impact of the American scientific enterprise. The American government, and DOE in particular, can capitalize on decades of investment and innovation, including those efforts initiated by the National Quantum Initiative Act. Chairman Babin, Ranking Member Lofgren, and members of this committee, thank you again for the opportunity to testify before you today. I look forward to our discussion and answering your questions.
Thank you, Dr. Crowder. Some of you all may be wondering what all the buzzers are about. They have just called votes, so I'm going to recess this committee until, be subject to the call of the chair until after votes. Thank you. The Committee on Science, Space, and Technology will now come back to order. Thank you. Let's see, I want to also thank the witnesses for their testimony, and now I want to recognize myself for 5 minutes for a series of questions. Dr. Kushmerek, China is racing to shape global technology standards, and advances in quantum computing could put existing cryptography methods at grave risk. How is NIST ensuring the U.S. leads in post-quantum cryptography standards, and where are the biggest gaps in our readiness, please?
Thank you, Mr. Chairman. So as already discussed, NIST released 3 standards, post-quantum cryptography standards, which are known to be resistant to a quantum attack, basically a Shor's algorithm attack. We are currently working to kind of, in the international standards arena, to create international standards so they can be adopted across the world. And finally, for domestic, we're working with over 50 industry partners and other agencies to figure out the best way to deploy into our systems. So I think those are where we're really pushing right now.
Okay, thank you very much. Dr. Clampin, the Artemis II mission will soon launch, sending astronauts around the moon for the first time in more than 50 years. However, the U.S. is not alone in its interest in lunar exploration, with China planning to send taikonauts to the moon by the end of this decade. How could quantum technology support these future missions? How is China's space program using quantum technology? And are there lessons the U.S. should draw from that utilization? And if you want me to, I'll repeat those. There's 3 of them. Okay.
The areas that NASA is working on that are in direct support of Artemis and the exploration objectives include what I would say are the quantum sensing applications, and examples include position and navigation, and that comes back to things like quantum magnetometers, quantum clocks, and there are other areas such as quantum sensing, imaging that I spoke of earlier, where we can actually do remote sensing of the moon, looking for specific minerals, etc., using this technology, which allows us to image and obtain very detailed spectroscopic fingerprints, if you like, of the moon's surface. In addition, we're also working on gyros, and that again is, quantum sensors allow us to get much better performance from gyros that we can get with conventional technologies, and then also optical communications. And right. Optical communications use our quantum sensors for the deep space applications.
Yes, sir. And then how is China utilizing quantum technology?
Well, we know that I'm not going to talk about communication because I think you've heard about that to a large extent. So China is developing some of these same capabilities, in particular gyros and position and navigation, because they are very important if you're going to establish a permanent presence at the moon. China does have a quantum communication satellite that was launched in 2016 called MICEUS, that's been doing very straightforward demonstrations of entanglement between space and ground. NASA is also doing similar experiments, such as the SEEK experiment that we conducted on ISS.
Okay, thank you very much. And Dr. Crowder, last month, this committee heard testimony from Undersecretary Gill on the Genesis mission and the establishment of the Office of AI and Quantum at DOE. How do these efforts avoid bureaucratic duplication and help accelerate progress toward the administration's quantum strategy?
Yes, thank you for your question. I want to first start by saying I really look forward to how the Genesis mission will reinforce American leadership in quantum information science, in AI, and high-performance computing. The Genesis mission is meant to simultaneously build a platform while also constructing scientific and engineering challenges in energy, national security, and discovery science. The department released its realignment plans to create these new offices, and They will support quantum information science, but also deliver capabilities to the nation. The Office of Science is going to continue to push the forefront of R&D while these offices deliver that capability.
Thank you. And Dr. Gonzalez, how is NSF partnering with other federal agencies to advance the administration's quantum priorities?
So thank you for the question. We partner in many ways. We partner indirectly through the researchers that we fund. That's a big part of the partnership, co-use of facilities and things of that sort. And we also partner coordinate through the NSTC subcommittee, and which is a coordination body that you've heard about. In addition, we have specific partnerships. We have partnership with NIH on quantum sensing. So we have the whole gamut of partnerships.
Thank you very much, and I'm out of time, so our next, I recognize Representative Bonamici from Oregon.
Thank you, Mr. Chairman, and thank you to the esteemed witnesses for being here and for your expertise. I discern that at least two of the witnesses, half of the panel, appear to be immigrants, and I want to thank you for exemplifying the contributions of immigrants to our economy, to our scientific enterprise, and to our communities. So thank you. Quantum science, we know, will shape the next century of scientific discovery, and the United States still holds a narrow lead. Whether we can hold onto that lead will depend on having people who are educated through sustained federal investments, students, technicians, engineers, and researchers. And at the same time, this administration talks about quantum dominance. It has slashed agency budgets, shed expert staff, frozen grants, and destabilized the workforce pipelines that quantum leadership requires. I'm a member of the Education Committee as well, very concerned about what's happening with higher education. We can't win a global technology race by hollowing out the institutions that recruit, educate, and retain talent. So Dr. Kushmerek, NIST supports, of course, the Quantum Economic Development Consortium, QEDC, which convenes leaders to identify needs in the quantum workforce. So what specific workforce challenges pose the greatest threat to U.S. quantum leadership right now, and which of those can Congress most easily and rapidly address?
Thank you for the question. So yes, the QEDC has polled its members, the industry, the quantum industry directly, to really understand where these challenges are. And it's not just in quantum physicists kind of leading the efforts, it's really all the way through to engineers and technicians and people at all levels. So I really think we need a whole government effort to kind of increase the pipeline. I mean, we need to
Absolutely.
increase the pipeline, and through certificates to degrees and other activities. So yeah, I think that's where I would go.
And reducing the cost of higher education is on the list of many of my colleagues and myself, because those doors of opportunity should be open to everyone who chooses to attend higher education. Dr. Gonzalez, graduate physics enrollment fell sharply in 2025, and international students who make up a large share of the quantum pipeline are increasingly hesitant to study in the United States or to stay in the United States. So I'm going to ask you, what will quantum look like in the U.S. 5 years from now if these delayed and frozen awards and agency staffing losses and reckless immigration and student visa policies continue?
Thank you for the question. I think that for us, quantum, for the NSF, quantum is a priority for the agency, and we'll do everything we can to keep it down, to deliver on that priority. It is right now. It's difficult to the first thing you mentioned about the grad students to predict what that will look at in a few years. But it's not just physics that we need to bring into the fold. There's computer scientists, engineers, material scientists, the whole range of disciplines that make quantum happen, as you mentioned.
I appreciate that. And if Congress does reauthorize the National Quantum Initiative, but the agencies lack the appropriate staff to manage the grants or to review proposals, what happens to those workforce pathways?
So one thing I will say about the NSF, we have great staff, and we are resilient. We're adapting to the changing situation, and so folks are sort of contributing everything they can.
I appreciate that. And it just, again, we need to open up those doors of opportunity to higher education, and that is something this administration has not made a priority. The Higher Education Act back in the 1960s, when President Johnson signed it, talked about opening those doors. There's so much potential out there, but if people can't afford to get the education, they won't be able to join the important workforce. We know that quantum leadership grows from classrooms and laboratories and a workforce that can trust the federal government to show up consistently. And if we cut that funding, if we shed the expertise, and if we destabilize these educational pipelines, talent will leave. And competitors will surge ahead. So real leadership means investing in the people, protecting the scientific capacity, and matching our quantum ambitions with the resources we need to accomplish them. Thank you, and I yield back.
Now I'd like to recognize gentleman from Tennessee, Representative Fleischman.
Thank you, Mr. Chairman, and I want to thank this distinguished panel for being here today, and a job well done. Before I go to my questions, I would like to make a statement. As most of you know, I represent the great people of the 3rd District of Tennessee, including the greatest mid-sized city in America, Chattanooga. I would like to make a remark regarding the quantum work being done in my own district. Chattanooga made history as the first city in America to launch a commercial quantum network. Chattanooga's leadership in applied quantum innovation is anchored by the Electric Power Board's ownership and operation of a commercially available quantum computer developed in partnership with IonQ and physically located in Chattanooga. These real-world assets support the University of Tennessee at Chattanooga in advancing workforce development and applied research through its Quantum Center, including hands-on access to a quantum networking node that allows students and researchers to train and operate in a live environment. In parallel, creating quantum ecosystem that has led to recruiting a research commercialization partnership with Vanderbilt University that connects academic research to deployable, market-ready applications. Together, this model demonstrates how targeted federal investment can serve as a catalyst that allows regional quantum ecosystems like this one to grow faster, scale responsibly, and deliver real economic and workforce development. With that, Dr. Crowder, I'm going to ask you my first question. In past years, the Department of Energy has advertised funding opportunities through Funding Opportunity Announcement, FOAs, or what we call lab calls. But these channels have been largely quiet this past year. How can stakeholders best keep informed of and respond to DOE opportunities? Thank you.
Yes, thank you for your question. The Department of Energy regularly puts out notice of funding opportunities. We have a couple of current ones open right now, or they maybe just recently closed. We also have an open call right now where we have added error correction an error correction focus to our open call in the Office of Science. The best way to keep apprised of what we do is on our website. We post all of our calls on our website and usually put out press releases for them.
Thank you. A follow-up question, Doctor. Oak Ridge, which is also in my district and is my heart, of course, has been a long leader in quantum computing and is working in the private sector to deliver quantum computing at useful scale. NVIDIA recently delivered an NVL72 supercomputer to Oak Ridge, which will help quantum processors with error correction, accelerate algorithms, and can even help simulate a quantum computer with AI. Can you please speak to how AI, high-performance computing, and quantum computers are working together to make quantum computing useful? Can you also talk why it is important that labs like the Great Lab at Oak Ridge National Laboratory and DOE work with the private sector on this issue? Thank you.
Yes, I'd be happy to, Congressman. Thank you. First of all, I want to thank you for your leadership in QIS and of your support for Oak Ridge. There are really a myriad of ways that quantum and AI will work together. You mentioned a few of them yourself. They will it's very difficult to see what the end goal or what the end applications will ultimately be. There are some very promising ones that we see in the future, and you mentioned a few of them, like error correction, the search for quantum algorithms. But the builders of the ENIAC probably would have never thought that we'd be using computation today like we use it, and we're able to order pizzas from our phones, and it's just an extremely rapid acceleration. But we see AI advancing for advancing quantum systems, and we also see quantum systems advancing AI, taking the output of these experiments and directing them right into the workflow of AI computers.
Thank you very much. And once again, I commend the entire panel. And Mr. Chairman, I so appreciate your calling this hearing. It's most beneficial. I yield back.
Thank you very much. Now I'd like to recognize the Haley Stevens from the great state of Michigan.
Thank you, Mr. Chair. And as Congressman Fleischman reflected on his beloved Oak Ridge, in Michigan, we also envy the Tennessee Valley Authority and the energy resources that come along with it. As we think about our quantum future, we can't overlook energy needs and protecting consumers, as well as national directives. And so I really also want to applaud Congresswoman Marcy Kaptur for her leadership on the Great Lakes Authority to model what Mr. Fleischman's district and so many of his stakeholders in Tennessee have with the TVA. And of course, I also want to take a minute to recognize each and every single one of you. Your public service and dedication to this country's research missions as honorable, and it is very meaningful. And while recent events haven't always made it easy, your contributions are certainly quite profound. Dr. Kushmerek, you noted in your testimony about supply chain gaps being a major barrier to scaling domestic quantum, and NIST certainly has a long track record of strengthening manufacturing capabilities and supply chain readiness. We're so deeply proud of the manufacturing extension partnership networks, including how they mobilize small and mid-sized manufacturers, and they did so very expertly during the COVID-19 pandemic. And the centers are, already focusing on emerging technologies like quantum, and we see that the MEP centers in Michigan, our Michigan Manufacturing Technology Center, leading quantum companies and sourcing in the region, demonstrating the role that these networks can play in accelerating this technology. So, Dr. Kushmerek, do you mind elaborating on how quantum manufacturing accelerators that you described in your testimony, I took a couple of notes, will help address supply chain and manufacturing barriers in the United States?
Yes, thank you for the question. That's really one of the main focus that we see for the accelerators. Being able to transition technologies we have in our labs, either in NIST or the DOE national labs or in academia, pushing it out to these small and medium-sized businesses so they can develop it in partnership, this co-development idea, so that we can create, not just onshore, a domestic supply chain. And I agree, there's the long history of MEP, and we are well-positioned to help manufacturers.
Yeah, and it's also of note that sitting in our audience is a former Undersecretary of Commerce and head of NIST, Dr. Phil Singerman, who remains a very active participant in our innovation ecosystem, and we're grateful for his presence here today. Also, the long-term competitiveness of Michigan manufacturing relies on advancements in material science. So, for example, the ability to design better materials that have made our cars lighter and safer and more sustainable, the benefit of material advancements that span manufacturing, the agriculture industry, healthcare, energy, and aerospace. Yet material science is a complex process that demands lots of computational power. And it's an area where quantum can provide a lot of benefits. And this is why I introduced the Quantum in Practice Act alongside Randy Feenstra, congressman from Iowa. to ensure quantum modeling and SIM are included in our federal quantum programs. And we've got just about a minute left here, but I didn't know if some of the witnesses could chime in on how your respective agencies are approaching quantum modeling and simulation research and development. Maybe Dr. Clampman, you could start. We very much appreciated your testimony and perspectives.
Thank you. I think from NASA's perspective, our primary approach to quantum computing right now is really how it will be applied to modeling in the future. And we are doing a lot of work on understanding what kind of algorithms we would need to apply quantum computing to areas such as earth science and other remote sensing applications.
Yeah, great. Well, thank you for that. And Mr. Chair, a long conversation, but a lot of great work on quantum. So with that, I yield back.
Gentlelady yields back. I'd like to recognize the gentleman from California, Representative Fong.
Thank you, Mr. Chair. Thank you to the panelists for your testimony. Certainly, America's leadership in quantum science is not an abstract research goal. It's a strategic necessity tied directly to our economy, our security, and our future. If I could start with you, Dr. Clampman, how does NASA see quantum technologies delivering concrete mission advantages in the next 5 to 10 years? And where does quantum give the United States a decisive edge in space exploration that our adversaries like China can't easily replicate?
So thank you for the question. You asked where we see this going. I think I said in my testimony that for us, the key area right now is quantum sensing, because in every area of measurement you look at, quantum sensing gives you that jump in capability that allows you to address new scientific problems, or gives you the additional capabilities you need to really pursue the exploration agenda that we're following, to the moon and then on to Mars. So we're really focused on all aspects of remote sensing, whether it's building magnetometers to understand magnetic fields. NASA loves these things because not only do they give us a factor of 10 improvement in performance, but they're self-calibrating, so they also save time and money as we build spacecraft. And all of the areas of sensing, quantum sensing that we're looking at have applications such as remote sensing that also will feed into the broader space economy.
Okay. And then to build off of my colleague from Michigan, and when in discussing the supply chain, and I'm sure I'm welcome to the open this to the rest of the panel as well, but specifically for NASA, are there critical quantum components or materials that NASA relies on that are sourced overseas, and does that pose as a strategic risk?
I am not aware of any at this moment. Some of our quantum sensors we actually build in-house at NASA. Many are done in partnership with U.S. industry.
Okay. Does anyone else want to?
Academia.
Thank you. Anyone else want to jump in on the supply chain question in terms of, do we source things overseas that we need to? Yes, Dr.
Yeah, thank you for the question. Currently, the supply chain is global in nature, very similar to the classical information technologies that we interact with every day. I think one thing that we can do and we need to do is understand what technologies and what materials we need to work hard to onshore and friendshore so that we can control that destiny and not cede too much control of it to our adversarial nations, and work to make sure that we have the right materials and the right processes in the U.S.
And just to follow up, has that inventory or inventorying been done?
There have been a variety of inventorying efforts across the federal government. For a variety of end uses, and I think that bringing together in a holistic approach some of these efforts would be a benefit, and we do that sometimes even currently through our subcommittees on the NSTC that were established by the NQI Act.
Sure. And this may be something that we might want to facilitate. I mean, I think supply chain resiliency is going to be important, not only from quantum, but on all the emerging technologies, whether it's quantum or AI. If I could stay with you, Dr. Crowder, what technical milestones must be achieved before quantum networking moves from experimental test beds to national scale infrastructure? And what is the biggest obstacle preventing quantum research centers right now from transitioning technologies into real world deployment?
Well, I'll stick with the networking for a minute. I think that the most exciting applications of quantum networking right now is distributing quantum information between quantum technologies. So think about connecting computing modules, computing chips, cryostats that have those chips inside them, and sensors. And so I think right now, what I'm most excited about is being able to do data center scale, so think intranet, not internet, of connecting quantum technologies.
And just my time's running out, but one last question, Dr. Crowder. How will the Genesis mission and the creation of the AIQ office accelerate quantum progress, and what should Congress expect within the next 5 years?
The delivery of capabilities.
Simple enough. With that, I'll yield.
Gentleman yields. I'd like to recognize the Representative Salinas from Oregon.
Thank you, Chair Babin and Ranking Member Lofgren, for the hearing today, and thank you to our witnesses. As we've worked quantum the past couple of years, I've really tried to focus on what workforce development looks like and at all levels of the workforce, not just PhDs. I have a bill with Mr. Baird to provide instrumentation colleges and universities the tools that they need for that practical training, and I was thrilled to secure over $1 million in our latest funding bill for Oregon Tech to acquire some of that instrumentation, so it'll allow them to provide some hands-on learning experiences for our undergraduate students. Starting with you, Dr. Gonzalez, at our last hearing, one of our witnesses suggested programs like NSF's Advanced Technology Education Program could be paired with those instrumentation investments to better support the quantum technical workforce. Can you share how ATE program may already be supporting the field and what additional investments or flexibilities could actually help maximize its potential to support quantum workforce developments?
So thank you for the question. I think the ATE is a great program because it bridges that gap. I do not have with me numbers on how many of these ATE awards have directly supported quantum, so I'll be happy to provide that to you at a later time.
Thank you.
Thank you.
And this next question is for the entire panel. Regional, technical, and community colleges often lead the way on training at these diverse levels of the workforce, and they serve diverse population students too. I worry that the administration right now, the attacks on diversity, are limiting those opportunities for these institutions and limiting my constituents' access to the jobs of the future. Could each of you tell me what specifically you are doing to recruit and retain quantum talent from across the country and across demographics?
Thank you for the question. So yeah, I mean, we are in a workforce shortage, plain and simple. We do not have enough domestic or even international talent to fill all the jobs. So at NIST, we look to hire, where we can. We look across the whole country, and we also welcome in foreign guest researchers when needed to help support this effort. And I fully agree that community colleges can be a great jump-off point in potentially partnering with industry to identify what's the right niche, if you will, for how they kind of get the training.
Thank you.
So for NSF, workforce is part of everything we do, and at all levels. And just for university, undergrad and graduate, we support almost 10,000 people just working on QIS. We recognize that if we're really going to be building the quantum future, we need to have the folks to work at all levels in this, and not just working in quantum companies, but working as practitioners, as users of the technology. And so we have several programs to sort of fatten the pipe for workforce. For example, Q12 is a program that we started in 2000 with OSTP to actually provide these opportunities, provide training, and it's a partnership also with the private sector. So that's one of the many things that we're doing.
Thank you. Dr. Clampin?
I'll just say that at NASA, we do not specifically look to hire people with expertise in quantum. We're really focused on hiring scientists and engineers who will allow us to pursue our science and exploration objectives. That said, we have a lot of partnerships both with industry and with academia where we're, growing, I think, in the areas that we're working in related to quantum, the next generation of, quantum expertise.
Thank you. Dr. Crowder?
Yeah, thank you. Workforce development is something that's extremely important to our department. And as Dr. Kushmerek indicated, the supply does not meet the demand. And so we have engaged in a variety of activities. One of them is through our centers, our 5 national QIS research centers that have together had over 1,500 collaborators through 115 universities and trained over 2,500 students. Another vector to have outreach with the community is our DOE facilities. They serve as a nexus for the workforce through their hackathons and in their training programs. They touch thousands of researchers, and they also provide the user facilities and our test beds provide hands-on provide access to hands-on technologies for students and senior scientists and technicians to work on.
Thank you. My time has expired. Thank you all. I yield back.
Yields back, and I'd like to recognize the representative from Georgia, Dr. McCormick.
Good afternoon, and thank you for being here today. This is an extremely exciting topic. Quantum technology is something that took me a long time to grasp. I'm sure not to the extent that you all have already overlooked this and helped us and guided us in this conversation. Really important that you're here today. One of the things that we've talked about is progress in quantum. And I want to define that. What is progress in quantum? Because I think it's ill-defined. And one of the great things is we are seeing progress, and it's actually being applied right now. Most people don't realize we're actually applying quantum technologies already. But what is the marker? And I wanted to ask you, Mr. Kushmerek, Dr. Kushmerek, what do you define as progress, and where do we need to go from here?
I mean, progress is impact, is in a simple sense. So, developing new quantum computers, quantum sensors that directly have real-world impact for U.S. citizens is how I see progress. And we are moving along that chain. From a metrics perspective, we need to get away from quantum computing where we're just talking about the number of qubits, but really what systems can solve meaningful scientific problems. And that's a way for us to kind of gauge where the progress is.
And where do you think we're on that scale right now as far as what things are we getting in the way of? What things are we helping with? And like as far as its application, I know it's limitless. I get that. There's no bar on the 100%. But where do you think we are as far as incorporating that technology into what we're actually accomplishing right now?
I think we're well along the way. For quantum computing in particular, when we started the NQI, we were in the noisy intermediate scale quantum regime where there was just hard to do things. And now we have demonstrations of error correction in quantum systems. So we have made tremendous progress, and it still needs to advance, but I think we're well along the way.
Okay, great. Another big thing I have a question on is our application to students. We obviously have a lot of students from all over the world right now studying here in America, 1 million basically, 250,000 from China. We have agreements now that may push it upward to 600,000. Very concerned, Dr. Gonzalez, where we're going with that. Right now we're basically educating our competitors, sending back to China where you have already 47% of all AI researchers, 50% of all patents, and yes, they're behind us, but they're trying to close the gap very much. What do you think we can do better on that?
Thank you for the question. Well, I think that if there's a concern about research security, we can actually deal with that, and we are at the moment. Certainly, I think all the agencies are.
What do you mean by dealing with it?
Meaning putting in practice, executing the policies and practices that protect our research, protect our intellectual property.
So the problem I see though is when they come over here, and yeah, I know they're not able to bring our research back to their countries with them, but they have it up here, and they're learning the most advanced technologies. I mean, you have 2 AI columns being researched at Georgia Tech right now with a tremendous number of foreign students who then graduate, don't stay here, go back to their countries, whether it be China or India or wherever else. How do we protect our technologies? What are we going to do to make sure that we're not basically putting other countries at a peer level, if not ahead of us in the future?
That's a very important policy question that I think it's outside my jurisdiction.
Anybody else want to take a crack at that? Because I think that's one of the more important questions we have facing ourselves right now. Obviously, we have an energy component of technologies. We have an application. But training our competitors at a massive scale. Anybody want to talk about that? It's a tough one, isn't it? Okay, we'll move on to the next one. That's something maybe we as congressmen maybe need to have a better discussion on, since we don't have, even our experts are a bit confounded on that answer. I get it. Dr. Crowder, how do you plan to engage the nation's top universities to ensure our success in quantum? What can we do better?
Thank you for the question. As I mentioned, our centers engage over 100 universities across the country. We had, it's an anecdote I like to tell, we had to get reviewers from places we didn't normally get reviewers when we recompeted the centers, because so many of our quantum information science experts were already intertwined with the centers. So what we can do is we can continue to use the university pipeline to generate the innovation engine that it is and provide new and brilliant ideas for how we can push the forefront of science, take that into the Department of Energy, start developing test beds for the technologies that need test beds, and start putting those into user facilities as they mature, and keep that innovation cycle continuing to turn.
Great. I'm out of time. I could talk to you guys all day because I love this topic. Thanks for coming in today. With that, I yield.
Gentleman yields. Now I recognize Representative Fushi from North Carolina.
Thank you, Mr. Chair, and thank you to our witnesses for being here today. North Carolina has strong leadership in quantum science, with institutions like the Duke Quantum Center and NC State helping prepare thousands of students each year for careers in science and engineering. But maintaining U.S. leadership in quantum and translating that leadership into economic growth and good-paying jobs requires a strong talent pipeline that starts in K-12 and extends through advanced research careers. Programs like the National Q-12 Education Program, supported by NSF, and bipartisan efforts such as the QLIC Act that I introduced with Congressman Obernolte are important steps in that direction. As Congress works to reauthorize the National Quantum Initiative, can each of the panelists comment on how NQI is supporting quantum education and workforce development at every level, and what gaps remain in preparing a quantum-ready workforce nationwide?
Thank you for the question. At NIST, our contribution to workforce development really is in training the next generation of cutting-edge scientists. So through our joint institutes with academic institutions, we have students and postdocs and, that really kind of are learning precision measurements and then go out and become leaders in the field and in the different technology areas. So that's primarily where we fit in the stack, if you want to think of it that way.
Sorry. At the NSF, thank you for the question. At the NSF, you already mentioned the Q12 program. But as in the case of NIST, we also have a core about 10,000 from undergraduate to senior researchers that we support at universities. And I also want to acknowledge that North Carolina and Duke is a great center for quantum for NSF. We funded, even before the NQI, project called STACK, which brings a full stack of quantum to the game. So thank you for that.
Thank you.
I'll just say that the NASA, we see our contribution as training the next generation of space science and space engineers and contributing to the U.S. economy, and not just within NASA centers, but also within academia and within industry as we work in partnership with them. And I'll just mention that one of the hooks, if you like, that really engages people is the mission work that NASA does. There's a lot of excitement around our science programs and our exploration program, and that's a really great hook for getting people engaged and bringing in the next generation.
I'd like to address your second part of the question, which is the gap, and that is we, bar none, just need to train more people across the talent spectrum, senior scientists, technicians, junior scientists, and make sure that we are able to place these people in good jobs once they actually get trained. I think another part of that is making parents understand that these will be good jobs when they graduate. They will learn a variety of skills from computer science, mathematics, physics, electrical engineering. You will not have a hard time finding a job if you learn these skills, and you will be able to contribute to the quantum information science technology pipeline.
Thank you. Dr. Crowder, we'll stay with you. In December, the Department of Energy sent formal technical assistance to the committee to support our efforts to reauthorize the National Quantum Initiative Act. One of DOE's proposals was for Congress to provide quantum-related prize challenge authority to all executive branch agencies that sit on the National Science and Technology Council Subcommittee on Quantum Information Science. I'd like to hear more about this proposal and why DOE believes it would benefit quantum innovation. In the department's view, how would prize challenges help to advance innovation in quantum computing and quantum science?
Yes, thank you for the question. The Department of Energy is excited about using a variety of programmatic mechanisms to drive the field forward. We've talked a little bit about our notices of funding opportunities, and the prize challenge would just be another mechanism to drive the field forward, both in potential algorithmic designs, hardware designs, and it just gives us more flexibility to push the forefront of the field.
That's my time. Thanks.
Thank you very much. And now I'd like to recognize Representative Biggs from South Carolina.
Thank you, Chairman Babin, and thank you to our panelists for being here today. Quantum technology has the potential to revolutionize science and computing. Lightning-fast computers, secure communication, GPS-independent navigation, enhanced medical imaging, and advanced cryptography are just a few of the uses of mature quantum ecosystem. For these reasons, winning the quantum race is vital for America's national security. I am concerned that many quantum companies are multinational, and we can't count on them in times of crisis to have America's best interest at heart. Likewise, I believe that only U.S. citizens should be involved in sensitive quantum research at our universities. Just recently, the United States granted a 100% American-owned South Carolina company the patent for quantum-enhanced radar technology. That substantially overcomes current radar limitations and will enable operations in GPS-denied environments. So my question is, as far as the expenditure of U.S. taxpayer funds is concerned, what will you do to prioritize working with 100% American-owned quantum companies with new technologies focused on winning the quantum race for the United States? And I'd love to hear from each of you.
Thank you for the question. So one area where NIST in particular is looking to help in this extent is through our accelerator program. We're looking to build a domestic pipeline for the supply chain. So we're helping to grow these domestic companies here in the U.S. so that we have these capabilities going forward, so that we aren't reliant on other nations or other companies.
So yeah, I agree with that. Thank you for the question. I agree with what Dr. Kishmer just said. If we're going to advance quantum, at least for now, we need to just use the supply chain we have. Looking forward, then we can secure it. We can think about the research security equivalent in the supply chain. Just to say, for the NSF, we only fund, essentially directly, we only fund U.S. researchers, even when they're international partnerships. So yeah.
So for NASA, I'll just say, echo my colleague's comments. You know, we only fund U.S. researchers, and when we fund the development of missions and, you know, flight hardware, we always are sort of constrained already by ITAR regulations, which have place limitations on who we can and cannot place contracts with, as we're thinking about, who we're going to partner with.
I'll say that the DOE takes strategic competition and emerging technologies very seriously and views the diversion of unclassified taxpayer-funded research as a significant threat to the U.S. economic and national prosperity. America's global leadership in science technology is founded on our unique strengths of our open scientific enterprise, and the DOE aims to balance the security risks of collaboration with the need to preserve America's scientific and technological edge.
Thank you. Cybersecurity and advanced cryptography will also be crucial in the quantum age. As the leading sponsor of this Cyber Pivot Act, I believe we need a robust career development system for cybersecurity. Cybersecurity relies on secure cryptography to keep data safe. In the sake of time, I'll just kind of get to the question, how will the advent of quantum computers change cryptography and cybersecurity, and what are the risks of not being the first nation to achieve quantum computing and cryptography? And I'll leave it open to whoever feels best to answer.
Yeah, so NIST in 2024 released 3 post-quantum cryptography algorithms to specifically protect our IT systems from a quantum computer attack. I fully agree that we need to make sure we have the workforce in that area as well to implement this. And we're really focused now on working with industry and other government agencies to deploy it. We have the standards, but until it's out there in products in the system, we're still vulnerable.
Thank you. My time has expired, so I yield back.
Gentleman yields back. I'd like to recognize Representative Amo from Rhode Island, please.
Thank you, Chair Babin, and then thank you for your leadership in holding today's hearing on America's leadership in quantum technology. And I'm really excited to be in front of this group of great thought leaders and public servants. It's not often that you get 3- and 4-letter agencies that create and contribute so much to not just the things that are important to us today, but leading the way for tomorrow. So I'm grateful to see you. Because, as you know, nearly 70 years ago, the United States became locked in competition with the Soviet Union, the space race, the Sputnik moment, and we won. And today, a new frontier demands our national attention, and that's quantum computing. And it is heartening to hear the bipartisan agreement that the United States must win this race. Even President Trump ranked quantum information science and technology second on his research and development priority list for fiscal year 2027. We agree on this. And the federal government has a critical role to play in reaching the next frontier of quantum innovation. And if we're to make this an American century, which I am certain it will be, we need to invest in our quantum workforce of today while growing the pipeline of the quantum workforce of tomorrow. You've heard that through line with the previous speakers. And despite this obvious reality, however, and his stated commitment to quantum innovation, President Trump's agenda has thrown a wrench in our pursuit of another American century. He has decimated our federal scientific workforce. From November 2024 to November 2025, there was a 29% decrease in federal civilian employees at NSF, a 16% decrease at federal civilian employees at NIST. And it doesn't stop there. Approximately 1/5 of NASA federal employees agreed to leave an agency they all probably love, under deferred resignation and early retirement. We need to invest in brilliant scientists, not fire them en masse. That's got to be a guiding statement. And investing at every level of the workforce will ensure that the United States can win the quantum race, just as the investments in our workforce ensured that we won the space race. But President Trump isn't doing that. He's attacking our pipeline of research talent from start to finish. Not only is he firing experts from the federal workforce, he's discouraging top-tier international talent from coming to the United States to contribute to the next generation of research. And that's seen in this aggressive immigration enforcement and sweeping attacks on international students, leading to a 12% decrease in international graduate student enrollment last fall. Why would the best and brightest come here when we've made them feel unwelcome? Why are we letting tomorrow's quantum talent go elsewhere? I know I'm preaching to the choir. You are seeing this and experiencing this firsthand. So this is a yes or no question for everyone. Are foreign-born scientists an important part of the U.S. quantum ecosystem? Starting with Dr. Kaczmarek.
Yes, they are.
I think yes, they are, and I think all the best talent is what moves us forward.
I'll just say yes, they are.
A month ago, you heard from my boss, who is an immigrant, and so I would say, yes, they are. I'm glad he and people like him are batting for our team.
Yes, and I'm ardent to hear that, because we need to level set on our values and what's so important. And since we've stopped recruiting and retaining the top talent, our adversaries have stepped up their efforts. According to CNN last year, more than 40 rising and established scientists left the U.S. last year to go to Chinese research institutions. And we can't afford to export the next great mind in quantum science like we're exporting now and allowing the sale of H200 chips. It's short-sighted. It only accomplishes one thing: gives up our strategic advantage. We can't do that. And right now, experts estimate that the Chinese government is investing more than triple the United States in applied quantum science. Yet, in 2023, our domestic private investment in quantum startups was approximately 10 times larger than China. So to beat China in the innovation race, we need government and private industry working together, hand in glove, to complement each other's strengths and weaknesses. In the time that I have left, Dr. Kaczmarek, do you agree with this statement, and how would you encourage the federal government to foster private sector investment in quantum?
I completely agree. And I mean, NIST has a long history of working directly with industry, and they are investing. And through the QEDC, where we kind of convene industry perspectives, we see that. So we're directly interacting with them and seeing where the investments are needed, where federal funds are needed or federal insight is needed, and that's where we're going.
Yes. Well, look, I'm grateful for your minds and your contribution to the federal enterprise, and we need to do everything we can to support you to unlock the success that we will have in this next great American century in quantum science. So thank you, and I yield back.
Gentleman's time's expired. I'd like to recognize Dr. Kennedy from the great state of Utah.
Thank you, Chair Babin, and to the witnesses, thank you very much for being here with us today. Dr. Crowder, I'll start with you, if that's all right. I'd like to ask the role that the national labs are going to play in the Genesis mission, as well as the National Quantum Initiative, if you'd explain some of that connectivity.
Yes, I'd be glad to. Thank you for the question. The Genesis mission is really about delivering a product, a unique scientific instrument for the country. The national labs, our 40,000 scientists that are employed there, are a national resource to us, and we will continue to leverage them to deploy this capability. The one thing I want to say about the Genesis mission is that there's a moment when we can go past just staring up at the stars and build a telescope. And for quantum computing, that moment is now. It is time to start building the telescope. It is time to start peering past our horizon of what is known. And I think that is what the Genesis mission is about and what the Genesis mission hopes to deliver.
And our national labs will be a key part of that.
Absolutely. Our national labs are instrumental to the success of the DOE mission.
Thank you very much. Dr. Gonzalez, I have a question for you about, so Representative Riley and I are working together on a Boosting Rural STEM Pipeline Act to invest in skilled STEM educators who want to work in our rural communities. And I wanted to know what the federal government is doing to build that pipeline, particularly in rural communities, of our quantum capacity individuals who are going to take the place of those of us that are getting older and aging out from this work that we're doing.
Thank you for the question. We at NSF, I talked that workforce is everything that, it accompanies everything that we do. And also, we are very keenly aware of that there's talent everywhere across the nation, geographically. And we try to reach that talent as best as we can. One example, we have a Dear Colleague letter that's actually, it's called Amplifying STEM Education Investments in and with Rural and Remote Areas and Communities. It's not specifically on quantum, but it's one avenue that we can do. And we know we need as much talent as we can get to move us forward. So,
Thank you for that. And I'd also like to continue, Dr. Gonzalez, and the China competition that we have, and which subfields of quantum technology does China currently lead us in research output and quality, and how can we work to increase our ability to win in that race?
So I think, again, thank you for the question. This is an area that's highly in flux because the whole field is in flux. But I think in the last few years, if you look, the publications coming out of China have good quality, and they're out publishing us. Number of patents, the same story. And I think they have their early priority was communications. So, and therefore you heard about the MISHUS satellite back in 2016. But we are also clearly working in these areas across the country.
Thank you. Yeah. Dr. Clampin, I had a question for you about how China has integrated quantum research into their space program.
I think you just heard that, at the moment that's really focused on their MISHUS quantum communication. We're seeing more investment and papers being published in areas like use of manipulation of atoms or photons for instrumentation such as magnetometers and gyros. So we're seeing a growing interest in that area, which is the area where NASA is primarily focused right now.
And the research is quality research. You feel like it's reproducible, and it is something that is actually justifiably moving the agenda forward for the Chinese Communist Party, or is the research questionable in any fashion?
I'm not sure we can really speak to that because we're talking about hardware items, and the publications would suggest that they are functional and operational, but we don't have verification for that. So,
thank you. And Dr. Clampin, if you would continue on with the remaining time that I have and talk about the importance of microgravity research and advancing quantum, and how will NASA be working with commercial partners in regards to accelerating our efforts as we transition from the International Space Station.
So, as you noted, we will be transitioning away from space station. A lot of the work that we're doing in the area of fundamental physics for quantum right now, we feel is getting to the point where we will be doing the next stages of flight demonstrations. A good example is atom interferometry for quantum gravity radiometers. So those will ultimately transition to free-flying demonstrations and then operational missions. We are currently looking at ways that we can partner with commercial launch services to replicate some of the capabilities that we've had on space station going forward.
Thank you for that answer. I yield back, Mr. Chair.
Gentleman yields back. I'd like to recognize the representative from North Carolina, Representative Ross.
Thank you so much, Chairman Babin, for convening today's very important hearing, and thank you to our witnesses for being with us this morning. Actually, it's this afternoon now. The importance of U.S. leadership in quantum science technology cannot be overstated. From computing systems that can solve problems far beyond the reach of today's fastest supercomputers to ultra-secure communications and revolutionary advances in sensing and materials, quantum technologies promise to redefine the frontiers of innovation. As we've heard and American leadership in this field is essential, not only for economic competitiveness, but also for national security, healthcare, and global scientific influence. Continued investment and collaboration across government, academia, and industry will ensure that the United States remains at the forefront of this transformative area of science and shape the 21st century and beyond. At the heart of this national effort are institutions like North Carolina State University, and I'm glad that my colleague from Durham mentioned NC State, which I represent. Bold research and education initiatives are helping to build the quantum workforce and advance cutting-edge science. NC State's Quantum Initiative unites research in quantum computing, materials, and networking with robust education and workforce development. NC State researchers are leading major projects backed by the U.S. Department of Energy. Some include the exploration of next-generation hybrid quantum computing architectures that could reshape how quantum machines are built and used. And then in Durham, just 20 miles away, the Quantum Center at Duke is building one of the largest quantum computers in academia. Through interdisciplinary collaborations, these two universities in the Research Triangle are contributing to a vibrant quantum ecosystem while training the next generation of scientists and engineers who will carry forward America's legacy of innovation. But the progress is not guaranteed. And as you know, and my colleagues have mentioned, in recent years, the Trump administration has hindered advancements in quantum, creating uncertainty around research funding, weakening international scientific collaboration, and deprioritizing long-term investments in research. Quantum leadership requires stability, openness, and sustained commitment. The choices we make today will make a difference about whether or not we remain leaders. So Dr. Gonzalez, the National Science Foundation has long played a central role in advancing quantum science by supporting fundamental research, building multidisciplinary research centers, and fostering partnerships across universities, national labs, and industries through programs such as Quantum Leap. How does NSF view the role of partnerships with higher educational institutions, and NC State and Duke in particular, if you can speak to that, in advancing quantum research, and why are these collaborations critical for maintaining our leadership in quantum science and technology?
Thank you for that question, and I wish I had more time to tell you all about it, but I'll just highlight a few things. Absolutely. NC State, we have something called the QSEC tax, and I'm not going to spell it out, but it's to develop quantum sensors for agriculture. That's really, really important. So we're focused on the applications. We also have, they're also part of the National Quantum Virtual Laboratory together with Duke to develop a trapped ion, basically testbed in North Carolina. So we are, for us, universities is what we fund and is where we fund the innovation and the workforce. So it's absolutely crucial.
And in North Carolina, we've also had community colleges partner, particularly with NC State, and that helps address workforce needs. In my district, we've had a number of NSF grants. As a matter of fact, your predecessor came to visit a community college and look at what those students were doing. Are you still doing that work, and how robust is it?
Yeah, I believe we are. What really helps is when these partnerships come to us, already formed, not already formed, but already there's an interest expressed, and then we look at it and we may or may not fund it. So I think that's helpful, yes. But I agree, community colleges are key for bringing us to the quantum future.
Thank you, and I yield back.
Gentleman yields. I'd like to recognize now the representative from Tennessee, Mr. Van Epps.
Thank you, Mr. Chairman, and thank you to our witnesses for taking time today to share your expertise and insight. Quantum is inherently dual use, as we've been talking about, sensing, navigation, communications, and computing. Dr. Crowder, to start with you, in your view, for dual use, what is the single biggest obstacle to taking quantum technologies from a lab demonstration to a Department of War program of record?
Well, so I don't want to get too far out of my purview and speak for the Department of War. What I will say is just in general, some of the biggest obstacles is just scaling from a couple of logical qubits that are loosely connected to highly interconnected systems with 100, 200 logical qubits that can perform hundreds of millions of operations. Those require careful handoffs between academia, who build the foundations of the qubits that we use now, to government partnerships, programs, industrial performers, and integrating these technologies all together. One thing I will plug here is that the DOE does a great job at bringing Serial 1 chips to the user community to use and compute on. We've done that a variety of times, most recently with the Exascale computing program. And I think that is something that we would look forward to continuing to work towards with quantum computing.
Great, thank you. While significant attention has focused on quantum computing, we know quantum sensors and networking are prime opportunities as well. And Dr. Crowder, back to you. What is the administration's strategy for accelerating these applications alongside computing? And how should the reauthorized NQI direct resources towards sensor development and quantum network infrastructure?
Sensing is an incredibly important part of the Department of Energy's portfolio. We have our large interferometer at Fermilab that is going to help us detect new fundamental constants for physics and gravitational waves, dark matter. Similarly, networking is, again, very important to us. We want to be able to connect systems together, and we need quantum networks to do that. It is impractical to send quantum information over classical networks. And so we need to continue to push that forefront and look to interconnect heterogeneous systems at the data scale level so that we can actually extract this information and compute upon it.
Thank you. As we look at the next phase of the NQI, how do agencies plan to prioritize quantum applications for securing and optimizing critical infrastructure, particularly our energy grid? Yes, sir.
Thank you.
And anyone else after that, too.
Yeah. So the applications of quantum computation and quantum information science in general for the grid is nascent and needs to be explored. We have a variety of investments to explore that space. We, right now, I think, are very excited about the quantum applications of material science, chemistry, high-energy physics, and doing some of these simulations. There was a recent paper that came out of one of our user facilities, NERSC, that showed that about 50% of their calculations were on those subject matter or those domain sciences, and could likely be accelerated through quantum computation at the hundreds of logical qubits level.
Great, thank you. Anyone else yes, sir.
I'll just note that NASA is actually not part of the National Quantum Initiative, but just again reemphasize the importance of the work that we're doing developing quantum sensors for space applications and the future benefit that brings to the national space economy.
Great, thank you. Appreciate that.
Yeah.
Sir.
One thing I would like to point out that there's a lot of national security adjacent quantum-related technologies, and just something that definitely, in my mind, interesting is, for example, materials design, simulation and design. Imagine if we could design a high-temperature superconductor. It would not just apply to society as a whole, but it would also have other applications. Yeah.
Great, thank you.
Yeah, and to get back to the idea of supporting the grid and supporting critical infrastructure, one of the key components is timing and time dissemination. And this has a critical role in that. We're working with other agencies to provide GPS-independent timing for critical infrastructure so that we're able to maintain that.
Great. Thank you so much. Mr. Chairman, I yield back.
Gentleman yields. The Representative Foster from Illinois, you're now recognized for your questions.
Thank you, Mr. Chair, for convening this, and to our witnesses. I would just want to thank you all for, toughing it out, and as as scientists in the federal bureaucracy. It's not always an easy job, but it really matters to the scientists that are out there, doing their job every day. Let's see, the easy part of my question is you get to listen to a member of Congress thanking you for all of the everything you do for the area I represent. I represent Illinois, and one of the joys about representing Illinois is I get to brag about how Illinois has been a real national focal point for the development of quantum science and quantum computing. The entire state actually has become a proving ground for the field. This is shown through the Chicago Quantum Exchange, which leads both the Block Tech Hub, now funded by Mr. Kushmerek's Commerce colleagues at the Economic Development Agency, and the Quantum Connected Project, which is currently among the 15 finalists for the NSF Regional Innovation Award. NSF has also funded two NSF Quantum Leap Challenge Institutes, one for hybrid quantum architectures and networks led by the University of Illinois Urbana-Champaign, and one for the quantum sensing for biophysics and bioengineering led by the University of Chicago. These efforts and in-state development are giving legitimacy to our world-class educational institutions. Not only by providing the facilities, but training the scientists. And, that's one of the reasons I'm proud to represent the Chicago area, which for the 11th straight year has been #1 location for businesses to locate into, which I think is something that I cannot say often enough, given everything that's said about Chicago elsewhere. Anyway, so let's a couple of questions. When you're in deep R&D, you can let 1,000 flowers bloom, but when you start making large-scale systems, you have to place technological bets. Some examples of that are you have to decide if you're going to be looking at cryogenic technologies. For example, in the big quantum park that's under construction, a big part of that is a big set of cryo plants for cryogenic quantum computers, which might or not win the race for the most effective way to make qubits. And so you're at least threatened with stranded investments if you place your bets wrong. A similar thing when you're building the conventional part, the big supercomputer-like things that are the front ends of these large quantum engines. There's a trend in AI to go to smaller and less precise word widths, smaller precision floating points, which is probably going to be useless in quantum. So either you're going to have to continue to invest in, high precision floating point engines, or you're going to just try to ride along. And so you have to decide, are you going to just buy conventional off-the-shelf AI stuff, or something that's more optimized? And it's going to be, billions of dollars of investment eventually. So how do you deal with that? And any of you, with when you start to scale up, having to place these bets?
I think that is an extremely complex issue that you highlighted, and it's something that's at the forefront of the Department of Energy's mind. We need to be able to first be able to explore a few, or actually as many as possible, qubit technologies and platforms, and understand how they can scale and deliver capabilities. We are, order at least or two orders of magnitude away from being performant enough to provide scientifically useful calculations. And we need to be able to explore these platforms that have not yet been completely developed, and then neck down quickly to a few that can actually scale to scientific computation. I think you can do that through a variety of mechanisms. We talked to one of your earlier colleagues asked about the prize challenges, things like that. Milestone-based programs can also help with that.
Any other thoughts on this? 'Cause, this is what's tough. Yeah, go ahead. Hadi.
So I'll just say, in the case of NASA, our priorities are always driven by our exploration and scientific objectives. And we have a whole technology maturation process that underlies that ultimate priority. So we basically just treat these technologies, and I'll emphasize again, we're really focused right now on quantum sensing applications. We treat them like any other technology that we have to develop to the point where we can fly it. So, you know, we start with 1,000 flowers, but the process kind of weeds out the ones that we don't want to actually go forward with.
Yeah.
So I would say very quickly, thank you for the question. We know that there are technology choices to be made, and I think for us is de-risking early. So that means continue to support the fundamental research that is aligned to quantum, but still fundamental, because there might be things hiding in there that we might be able to use.
Yeah, well, you all have tough choices to make, and there's no substitute for having really high-quality minds making those choices, so thank you all.
Gentleman's time's expired. I'd like to recognize Representative Herodopoulos from Florida. You're recognized.
Thank you, Mr. Chairman, for the opportunity. And I would ask Dr. Clappett, if I could, the first question, if you don't mind. In your testimony, you mentioned that extreme space environment allows for unique quantum testing opportunities. One example is the NASA's Cold Atom Laboratory, which is hosted on board the International Space Station. And so the question is, what will happen to that Cold Atom Laboratory when the decommission potentially comes just a few years away?
So our goal with the work that's being done with the Cold Atom Lab, which is really developing techniques and understanding requirements for future instrumentation, the goal will be to transition some of that technology to free-flying space applications. And you know, the good example that I will give is the quantum gravity gradiometer, which requires manipulation of very cold atoms in order to make the measurements of gravity. So for the most part, a lot of the work that we're doing now will be transitioned to free-flying experiments. We are also exploring opportunities post-space station for other commercial launch services that would allow us to continue some development work when that was needed.
And just to follow up on that, so would you also consider using crewed or otherwise?
It's certainly a possibility, yes.
Okay, thank you. Next, I wanted to ask Dr. Kushmerek, if I could. You mentioned in the NIST work will help to secure the intellectual property of the United States. In particular, NIST will create accelerators, adaptive and flexible industry partnerships to develop and manufacture quantum products. How will these NIST accelerators promote dominance in quantum computing?
Thank you for that question. So the real plan here is to kind of co-develop with industry. The NIST and other government laboratories have the expertise and the technology. Industry is capable of commercializing it and pushing it out the door and creating that economic and quantum advantage and dominance that we're looking for. So that's the fundamentals of it.
And what are the barriers that are out there that might prevent some of these partnerships?
Well, there's not really barriers to prevent the partnerships. There's technological barriers in development of the different technologies.
So there's no bureaucratic limitations in your mind at this point?
I'm sure there are some, but none that pop up.
And there's no legislation that we could propose to accelerate some of the goals we're looking for?
I mean, in the National Quantum Initiative reauthorization, there is already a call out for what we are looking to do, but I would welcome working with your staff to kind of maybe strengthen that language if appropriate.
With that, Mr. Chairman, I appreciate the opportunity as always, and I yield back.
Gentleman yields, and now I'd like to recognize the gentleman from Virginia, Mr. Byer.
Mr. Chairman, thank you very much. And thank all of you for hanging in for 3 hours. We feel so fortunate to have NIST and NASA and the National Science Foundation and DOE, such talented people, well-educated people doing this. One of the main challenges facing the budding U.S. quantum industry is the supply chain and the choke points. And last year we had several companies talking about how the materials they needed had to come from Europe or Asia. We just saw what happened in Davos yesterday with this on-again, off-again trade war. 10% tariffs, 25% tariffs on our European allies, and then they're off again. I'd really like to know how, first of all, make the point that the tax is not just on American consumers, it's also on the American innovation economy. And Dr. Kushmerek, especially, has NIST heard from industry partners at QEDC about how the trade war is affecting American companies, and how do you help them through this?
Thank you for that question. And yes, the QDC has been polling its members, the U.S. quantum industry, and has learned a number of impacts from the tariffs, including, having to pay the import duties effectively, and how that's kind of disrupts their plans for research and development if now things are that much more expensive. So we have some of that data. We understand kind of mostly anecdotally where things are at. But yes, it does cause uncertainty, and uncertainty is bad for science.
Great, great. Thank you very much. Dr. Crowder, it's thrilled to have a William and Mary math and physics graduate with us. You said a lot of interesting things that feed into a lot of our concerns about the existential risk of artificial intelligence and artificial superintelligence specifically. You talk about scientific computing is at an inflection point. We're accelerating America's computing capability, but the quantum has the potential to revolutionize, and that distributed quantum computing would connect multiple processors to form a more powerful, unified quantum computing system. Given that even our best computer scientists don't know what's happening inside these neural networks, you talk to Sam Altman and Jack Clark, and they can't tell you why it works. Given that we don't know how consciousness evolves, and that we have not solved the alignment problem, how do we know that artificial superintelligence wants what we want? What's your perspective on making quantum computing, all the good stuff you're doing, how do we make sure that we don't lose control of it?
Thank you for your question. Quantum computing at its heart is good for two things that we know of right now. That's code breaking, and we'll stay away from that for now, and making things. We want to be able to do chemical simulations. We want to be able to do high-energy physics simulations and material science simulations. We can look past the scientific applications and look towards things like being able to create better fertilizers, better, more anti-corrosive materials that you could see transitioning to industry and making the American experience even better than it already is. And so I think that's what I think about when I think about how we can work to scale towards utility and scientifically relevant quantum computing.
Without a specific concern about quantum being an important part of developing artificial superintelligence?
Well, I think quantum is it fits into the high-performance AI supercomputing, quantum supercomputing. They fit together, but quantum computing is a fundamentally different paradigm. I can see us being able to use AI to improve quantum computers through error correction and algorithmic searches, and I can see us using quantum computing to improve AI, like feeding it information out of unique information that can't be produced from classical systems into artificial intelligences to even expand our ability to learn from them. And so I think those are how our department views those two playing together.
Thank you very much. Dr. Gonzalez, we've never passed a privacy law in 250 years here, but there's all excitement about how quantum computing can give us mechanisms to keep data secure. Do you see any hope about using quantum encryption to have a personal impact on Americans protecting their own data?
My personal opinion is yes, but at the time it will take some time to get those systems in a way that can be used in the way that you describe, I think, but yes.
I have 15 seconds left. I'm fascinated about a protein that turns into a functioning qubit.
So are we.
Can you talk just a little bit about
so this is one of the Quantum Leap Challenge Institutes that was funded at the University of Chicago, and they basically engineered a protein inside a cell to become a quantum biological qubit. And a qubit is sort of like because it's very sensitive to the environment around it. Then it can report all sorts of things from a cell. And you can imagine the applications of this years from now, and that's one of the killer apps in my mind for quantum sensing.
It certainly leads to an understanding of what a qubit is. But thank you.
Gentleman yields. Representative McLean Delaney, you are recognized for your questions.
So thank you to our chair and to our ranking members, and Thanks to our witnesses. I've been watching keenly this from my office this morning, and I really appreciate all of your testimonies. I really did like Rep. Byers' question on privacy, because I spent a lifetime in tech and policy protecting kids' privacy online, and I would love to see how quantum can be used to help in a whole host of areas to protect privacy. But I do want to give a special welcome to Dr. Kuczmarek from NIST. My colleagues know how proud I am of NIST because it calls Maryland's 6th Congressional District home, and that is where I represent, and so I'm so glad to have you here today. My state might be small in size, but it's massive in national and international quantum leadership. NIST expert researchers and scientists in my district in Gaithersburg and in Boulder, Colorado, pioneered the earliest quantum technologies and set national standards that have earned 4 Nobel Prizes. NIST created the first quantum logic gate in the 1990s. Last year, Governor Moore, who I was just with right now, launched Maryland's Capital of Quantum Initiative, a groundbreaking public-private partnership between our state, universities, private companies, and federal researchers, designed to leverage our highly skilled workforce and extensive expertise to help win the global quantum war. The initiatives of the past 2 decades of collaboration between NIST and the University of Maryland through Joint Quantum Institute, JQI, and I heard you all speaking about it earlier, turns theory into working experiments and ideas into products. As many of you have mentioned, our international competitors are doubling down on quantum research. Beyond quantum computing, China is racing ahead of communications and sensor development. I know that NIST and its partners from academia and industry have the ability to create this technology, and they need our support now more than ever in the face of the Trump administration's cutbacks on federal, on fundamental and foundational research. Our national security depends on not just innovation, but on production, and we have to be able to produce. So I just want to address our supply chains. Although the CHIPS and Science Act began the process of onshoring prediction and production here in the United States, quantum technologies require enabling components like lasers and cooling equipment. You mentioned that NIST pioneered many of these technologies, but U.S. researchers and companies rely heavily on imports from Europe and China, and tariffs and supply chain disruptions have only increased costs. So in a reauthorization of the National Quantum Institute, how can we cultivate a complete quantum ecosystem that includes domestic production for these enabling and auxiliary technologies? And I think I heard Rep. Fong also asked Tanner Crowder about this. And how can we identify and address gaps in technology production and workforce?
I'll take that, I guess. And thank you. We're very happy, and thank you for mentioning the Joint Institutes. I'm always happy to talk about our Joint Institutes.
Amazing.
Kind of working with academia directly has been key to NIST's success and leadership in quantum. So we're very happy about that. With respect to the supply chain, I mean, yes, there's a lot of U.S.-developed technology that now is manufactured overseas. We all know that. Really, one of the things we are looking for within the reauthorization is to kind of refocus and kind of onshore or develop new supply chains, really, not even just kind of duplicate what's there, but move past that. So through the Quantum Accelerator program, we're looking to focus on chip-scale lasers and modular small cryosystems that can be deployed in different ways as a change agent to kind of move forward.
Excellent. And then one more thing. In your testimony, you mentioned that NIST is already working to establish post-quantum encryption standards. How will NIST not only ensure that these standards exist, but they are deployed in a timely manner that keeps the U.S. ahead of our foreign adversaries?
Yes, thank you. So yes, we've developed and published 3 post-quantum cryptography standards. They are now being developed into international standards so that they can be incorporated across the globe, because if we need to communicate with somebody, we both have to have the same encryption. And the big challenge now is actually getting it deployed, getting it out into the world. And NIST is working with other agencies and industry to come up with best practices and different ways of implementing so that we can really keep our foot on the gas in that sense.
Thank you, and I yield back. And thank you to all of you. It was a really fascinating discussion.
sorry, I hit the wrong button. I want to thank all of our witnesses for your very valuable testimony, coming and sharing that with us, and as members for our questions. And the record will remain open for 10 days for additional comments and written questions from the members. So thanks again. We appreciate all of your services. Appreciate it. Hearing is adjourned.